Hello everyone, hope you all are doing good. I am Anjana from LearnoHub, the free learning platform where you can study math, science and SST absolutely free at learnohub.com. In today's class, we are going to discuss ICSE Class 10 Physics Chapter 7, Sound. We'll be discussing what natural vibrations are, damped vibrations and forced vibration. We'll be discussing about resonance and the characteristics of sound. Hope you all are ready for the session. Let's start. First one is natural vibration. What are natural vibrations? Just consider this case. Here you can see a pendulum which is fixed with a rigid support. Now here when you disturb, this is a mean position. O is a mean position. When you disturb slightly, what happens? It starts oscillating. There will be vibrations in this case. Okay, to and fro motions will be there. Okay, so here we have studied about amplitude, frequency and time period in the previous class. So amplitude is the maximum displacement. In this case, the amplitude will remain same from here to here, from here to here. This continuous motion is going to happen. That is, amplitude will remain the same. In case of a natural vibration, this natural vibration will always occur in vacuum, or it can also be called a free vibration. Okay, it will be happening in vacuum, not in any medium, because if there is a medium, then what happens is, if there is a medium, there will be some resistance created, there will be some external factors. Okay, without any external factors only, we can call it as a natural vibration. Vibration without the effect of any external factors. So when there is a medium, what happens? You can take, if air is a medium, then there is air resistance. Okay, due to this resistance, what happens? There will be chances of amplitude changing. The amplitude will decrease due to this resistance. Okay, here the amplitude will remain the same. So it is called a natural vibration. So you can define natural vibration as the periodic vibrations of a body in the absence of any external force on it are called natural vibrations. So for this natural vibration, the time period of this natural vibration is called the natural period and the frequency is called its natural frequency. And this frequency, it depends only on two factors, that is the size and shape of the body, not on any other factors but just the size and shape of the body. Okay, remember this important point, vacuum is important for natural vibration to happen. Not in any medium vibration that natural vibrations can happen. Clear? Now we'll take some examples for natural vibrations. So first one is, if the bob of a simple pendulum is displaced slightly from its mean position, it starts vibrating with its natural frequency. The same case which we have discussed here, you can see a bob. This is a bob of the simple pendulum. When it is displaced, what happens? You can see to and fro motions. It starts oscillating. Okay, now here this oscillation, during this oscillation will be having a maximum amplitude and the body will be having a natural frequency. How to calculate this natural frequency? This natural frequency can be calculated as F is equal to 1 by 2 pi root of G by L. So here G is acceleration due to gravity. What is the value on Earth's surface? What is the acceleration due to gravity? Yes, we have studied 9.8 meter per second square. Okay, then L. L is nothing but the length of pendulum. L is the length of pendulum. Therefore, the natural frequency depends on 1 by 2 pi root of G by L, which means here it depends on, frequency depends directly on the root of acceleration due to gravity and inversely on the root of length of the pendulum. Okay, so here you can understand that when length increases, frequency decreases. Acceleration due to gravity, we know it is a constant. Okay, so for example, if you are taking a pendulum of 1 meter length, in that case, G value we know is 9.8 meter per second square. Then you will be getting frequency F is equal to, when you calculate 1 by 2 pi root of 9.8 divided by 1, the value you will be getting approximately 0.5 and the unit is hertz. Okay, so different pendulums will be having different natural frequencies. Why? Because it depends. We can say that the acceleration due to gravity is a constant on the surface of Earth, but it depends mainly on the length. We said that the length increases, frequency decreases. Now, if we are considering different pendulums of different length, then it will be having different natural frequencies. One with the maximum length will be having minimum natural frequency, and one with minimum length will be having maximum natural frequency. Clear? Second example, load suspended from a spring when stretched and then released starts vibrating with its natural frequencies. So here you can see we have a spring. So the spring, we know it can be compressed, it can be expanded. Now what happens is here we are suspending a mass. Okay, when a mass is suspended, you can see a load which is suspended. What happens? The spring has expanded. You can see the expansion of spring. Initially this was the, so here you can see it has expanded, right? So during this expansion, what happens is there will be a natural frequency. Here expansion has happened to the spring. It will be having a natural frequency, and the natural frequency here, it can be calculated as F is equal to 1 by 2 pi root of K by M. Here K is a constant for a given spring. This K is called the spring constant or force constant. Okay, for the material, it is a constant value. So if you are taking two different springs, then it will be having two different spring constant. The value of K will be different. Next, it depends on the mass or the load. Okay, the load which is suspended. So how is it related? Spring constant increases, K value increases, natural frequency increases. That is, the one with more spring constant will be having more natural frequency. Dependence on the mass. When mass increases, what is happening? The natural frequency is decreasing. One with less mass will be having more natural frequencies. Understood? So if you know this, you can find the natural frequency in case of spring. Clear? When a tuning fork is stuck against a hard rubber pad, it vibrates with its natural frequency. So here you can see a tuning fork. When a tuning fork is taken and it is stuck against a rubber pad, or either this situation is also possible, you have a tuning fork and you are hitting with some material. What happens? It starts vibrating. During this vibration, longitudinal waves are there. Okay, along this longitudinal waves, the sound will start traveling and it will be reaching our ears. So this is what happens. So for each tuning fork, it will have a different natural frequencies. Natural frequency will be different for a different tuning forks. Okay, so we call it the pure note. That produced sound will be a pure note, and for different materials, the natural frequency will be different. Fourth one, when an air column in a flute or organ pipe is made to vibrate, it vibrates with its natural frequency, which is inversely proportional to the length of air column. So here, how do we use a flute? How does sound comes out of a flute? What is happening here? In this case, you can see that there are many holes. In these holes, vibrations are created. That is, you will be closing different holes to produce different notes. Okay, so here the natural frequency, it depends on length and is inversely proportional to the length of air column. So when the length, that is, when you are closing the different holes, the length is changing, length of air column is changing. Therefore, the frequency will also be changing. If the length of air column will increase, frequency will decrease. So this is a relation. So when you take an organ pipe, in case of organ pipe also the same thing is happening. One which is closed at both ends, one which is closed at just one end, open at both ends. In all these cases, different frequencies, different natural frequencies will be there, and they will be in different ratios. Okay. Fifth one, when a string instruments like sonometer, violin, etc. is plugged once, the transverse vibration of a definite natural frequencies are produced in the string. So here you might have played these instruments. So people who use musical instruments will know that different places you will be getting different notes, right? The sound produced will be different for all these instruments. So here the frequency, the natural frequency, that is when you just plug a string, what happens? It starts vibrating with its natural frequency. So this natural frequency is equal to 1 by 2L root of T by pi R square D. Let me explain what these are. L is the length. Okay. Then T is the tension that is created. R is the radius and D is the density. Here this pi R square D is nothing but it is the mass for unit length. Okay, mass per unit length. Clear? So here if you need to increase the frequency, what can be done? Frequency is inversely proportional to length. So by decreasing length, you can increase the natural frequency. Okay, then proportional to the root of tension. So when tension increases, what happens? By increasing the tension, you can increase the frequency. Okay, next, radius. Radius can be decreased when radius decreases because they are inversely proportional. Radius decreases, frequency increases. Okay, this is the case with the musical instruments. The natural frequency of musical instruments. So while striking, if you're producing more tension, what happens? The frequency is going to increase. Okay. Sixth, when we strike the keys of a piano, various strings are set in vibrations, each at its own natural frequency because they are of different thickness and under different tension. So you can see that in case of piano, you all have played piano, right? So while playing piano, when you touch each or when you press each of the keys, what happens? You will be hearing different sounds because here the thickness of the keys are different. Yes, thickness are also different. Also the tension that is created in the strings of these keys of piano will also be different. Due to this reason, what happens? The natural frequency of the keys will be different. A string of a given length stretched between its end under given tension can be made to vibrate in different modes by plucking the string at different points. So here you can see this is your string. Okay, when at the middle it is struck or when it is plugged at the middle, what happens? Up and down motion will be there. Okay, first it will be coming down, then going up. That is a single loop is formed. One loop is formed. Here the frequency is the natural frequency, that is F, the principal frequency of vibration. Now in this case, second case, here what happens is, let's say the total length is some 10 centimeter. Okay, now here in this case, we are going to plug the string at 1/4 of its length. Total length 1/4, that is 1/4 of 10 centimeter, which is 2.5 centimeter. So measuring 2.5 centimeter, if you are plugging the string at this point, what happens? This is how the loops will be formed. You will be getting 2 loops. Okay, in this case, the frequency will be called the first subsidiary frequency. Okay, first subsidiary frequency, which is equal to 2f. Now in this case, here 1/6 of the total length. You will be measuring 1/6 of the total length and then plug at that point. Then what happens? You will be getting 3 loops. Okay, here you will be getting 3 loops. In this case, the frequency will be 3f, or this is called the second subsidiary frequency. Okay, now in this case, you will be finding 1/8 of the length. Plug it at that point, you will be getting 4 different loops. Clear? Now in this case, you can understand that the frequencies here we got f, here it is 2f, here 3f, here 4f. So when you take the ratio, you will be getting 1:2, 2:3, 3:4. This is the ratios of the frequency. Now you can see that wavelength. What is wavelength? It is the distance between two consecutive crust or trough. So this completes a wave. This is a complete wave. Yes. So when you check here, you can see you just have half of the wave. Okay. So the total length will be equal to half of the wavelength, lambda divided by 2, because there is not a complete wave. Only half part is there. So here L will be equal to lambda by 2, or you will be having wavelength lambda is equal to 2 times L. Okay. Now take this case. Here it completes a wave. Okay. This is a complete wave. This part is lambda by 2. This part is lambda by 2. Okay. Therefore, L will be equal to lambda. Now this case, here you have lambda by 2. Here you have lambda by 2, here you have lambda by 2. Lambda by 2 plus lambda by 2 plus lambda by 2, which is 3 lambda by 2. Therefore, here the length L is equal to 3 lambda by 2, or lambda is 2L divided by 3. Lambda is equal to 2L divided by 3. We'll be taking these 3 cases. Now, what is the ratio of wavelengths then? Here, the lambda is equal to 2L. 2L is to, here lambda is equal to L. L is to, here lambda is equal to 2L divided by 3. 2L divided by 3. Okay. Now multiplying each with 3 in order to remove this 3 from the denominator. Okay. What do we get? 3 into 2, that is 6L is to 3L is to 3 and 3 gets cancelled, 2L. So you can remove these L's. So the ratio of wavelength is 6 is to 3 is to 2. Okay, we know that when frequency increases, wavelength decreases. So one with minimum frequency will be having maximum wavelength. So these are the ratio of wavelengths. Nature of the natural vibration. So here we have a graph. Amplitude and frequency of vibration remain same. We know in case of natural vibration, it is occurring in vacuum. The important condition, it will always occur in vacuum. Amplitude and frequency will remain the same. Just take the example of simple pendulum. Here what is happening? Just we are creating a disturbance and the amplitude is going to remain the same. Natural frequency is going to remain the same. So when you plot a graph between the displacement is taken on the y-axis and time along the x-axis. Okay, time along x-axis, you will be getting a graph in this way. Here this is the maximum amplitude. This is your amplitude. Maximum displacement is amplitude. Okay, then you have the wavelength between two consecutive crests or consecutive trough, you will be getting the wavelength. So when you measure at each stage, okay, you are performing the experiment, let's say for 1 second, 2 second, 3 second, 4 second, when you measure the amplitude, the displacement, the maximum displacement, when you measure, you will be getting the same. The height it goes will be the same. It's not going to change. So this is an ideal condition. Okay, and it happens only in the case of vacuum where there is no resistance. If there is some resistance, because in normal cases, ideal conditions don't exist. That is, if there is any resistance, let's see what happens. Here the amplitude will gradually decrease and finally the body will come to rest. So this is a normal case. Only in natural vibrations or when you take the ideal conditions, this is going to happen. We said about natural vibration which is happening only in the case of vacuum and there the conditions should be ideal conditions. Now in the normal case, normally what happens when you take the case of a simple pendulum, you are displacing from the mean position, you are taking the bob to a new position from its mean position. What happens? It will come here first, then it will go to the same height. After some time, that is the next time, it will be reaching here only, it won't go to the maximum height. And this side it will be reaching here, then here and here, here and here, here and here, and finally it comes to its mean position. This is a normal thing that is happening. When you take the case of a spring, you just compress it and release it. What happens? It keeps on vibrating. After some times what happens? The vibration will decrease and it will come to rest finally. You take the case of a tuning fork. What happens? It keeps vibrating. When you strike it, it keeps vibrating. After some times, there won't be any sound. There won't be any sound. It will come to rest. This is a normal case. And these vibration we can call the damped vibration. Here what actually happens? When time increases, with change in time, what is happening? The amplitude is decreasing. So here, just look at here. Here you can see that this is a maximum amplitude in the first bit. Okay, first vibration, this is a maximum amplitude. Next, what is happening? It is decreasing. The displacement is decreasing. Yes, displacement is decreasing. That is, the amplitude is decreasing in these cases. So when the amplitude decreases, you can call it as damped vibrations. So periodic vibration of a body of decreasing amplitude in presence of a resistive force are called damped vibration. Now remember, how does this decrease in amplitude happens? The decrease in amplitude is due to the resistive force. Here there will be air resistance. Okay, due to this air resistance, there will be some frictions created, there is some resistance created, and the amplitude will be continuously decreasing and the body will finally come to rest. Okay, in case of damped vibration, you will be studying about two important forces that is acting on the body. Forces acting on a vibrating body. One is the restoring force and the frictional force. What is restoring force? That is, when you take the case of a spring, you expand it or you compress it and release, it will have a natural tendency to come back to its original state. So this force that helps to come back, the body to come back to its original shape is called the restoring force. When you take the case of simple pendulum, if you just displace a bob, it will have a tendency to come to its mean position. So due to this restoring force, the body will come to its mean position. The second one is the frictional force. So frictional force, if you have the body in air, there will be some resistance created. Now it depends on this frictional force, it depends on the velocity at which the body is moving. Okay. We know that the body, when it is in motion, when it is vibrating, it will be having kinetic energy. Okay, it will be having kinetic energy. So this kinetic energy, because of this kinetic energy, the body can do work against the frictional force. Against frictional force, only if it is able to do work, it will be able to move, right? So therefore, this energy is used as, that is, it is changing into work done. Okay, it is changing to work for the body to continue in its motion. So since there is some dissipation of energy, there will be heat created. Okay, heat will be created and there is a loss of energy as heat. And due to this loss of energy, what is happening? The amplitude is decreasing. Okay, since there is a maximum energy is decreasing because of the work that is being done and the energy is getting converted to heat. Okay, in that case, amplitude will decrease. Okay, due to this decreasing amplitude, at last when finally all the energy is lost, the body won't be able to move and will come back to its mean position. Okay, so these are the two factors on which the vibrating body's forces, these are the two forces which are acting on the vibrating body. So the rate of energy loss, it depends on two factors. One is the medium, that is the surrounding temperature, humidity, viscosity of the medium, etc. On these factors, the rate of energy loss will depend. And the second factor is nothing but the body's shape and size. So when you take the graph, when you take a displacement time graph, so this is how the amplitude is changing. In this case, when time changes, what is happening? The amplitude is decreasing. Here initially, this is maximum amplitude. The amplitude decreases at each stage. And finally, there won't be any movement. There won't be any change. Okay, the body will come to the mean position. So the straight part is the mean position. Okay, with the change in time, time will be increasing. The body will be at rest. Examples of damped vibration. We have studied some examples for natural vibrations. So remember that natural vibration is only in vacuum. So when you take the actual conditions, this is going to be damped vibrations. Okay. So first example, when a slim branch of a tree is pulled and then released, it makes damped vibration. So when you take the slim branch of a tree, when you pull it, it will first come down, then go up. Again come down, again go up. So finally what happens? It will come to rest. Okay, so you have tried, right, when you have to just pluck some hibiscus from a hibiscus plant. In that case, if you are not able to reach it, you will go pull the tree, okay, pull the branch and pluck the hibiscus. After that, what is happening? You can see that the branch will keep vibrating. Now, the second example, a tuning fork when struck on a rubber pad executes damped vibration in air. That also you have seen, like you take a tuning fork and you strike it on a rubber pad. It keeps vibrating. You can hear the sound. The sound will decrease and finally the tuning fork will come to rest and no more the sound is heard. Third, a simple pendulum oscillating in air or any other medium execute damped vibration. In case of simple pendulum, what is happening? Initially it will go here, come, and what happens? The amplitude will go decreasing. Finally, it will come to its mean position. Okay, this is not a natural vibration. Remember, natural vibration, it is in vacuum. So here you have to remember which is oscillating in air or any other medium. There should be a medium, not in vacuum. In vacuum, there won't be any change in amplitude and it is going to be a natural vibration. The vibrations of a spring having a mass at its end in air are damped vibration. When you take a spring, that is, you just suspend a load, what happens? This is how initially the spring will be with the load. After some time, what happens? Decreases. The spring will start compressing. It will again compress and finally, it will come to its mean position. Okay. Let us now study the difference between natural vibrations and damped vibrations. First point, the amplitude of natural vibrations remains constant and the vibration continue forever. It is not going to stop. It will always continue and the amplitude is always a constant value. What about the case of a damped vibration? In damped vibration, the amplitude of a damped vibration gradually decreases and finally it will stop. With time, it is decreasing and ultimately the vibration ceases. Okay. Second point, there is no loss of energy in natural vibration. In natural vibration, because of that energy it is vibrating with the same amplitude. But when it comes to the case of damped vibration, in each vibration there is some loss of energy in the form of heat. The energy is lost in the form of heat. Okay. Third, no external force acts on the vibrating body. The vibrations are only under the restoring force. There is no external force that is acting on the body. Here, there is an external force. Yes, in addition to the restoring force, a frictional force or a damping force. This frictional force or damping force, we have said that this frictional force is creating the heat energy, and there is a work done for it to move. This heat energy will be lost, and finally the body will lose all its energy and come to rest on the body to oppose its motion. So the friction is creating, so there is a friction created. So against this friction there should be a work done. So the energy in the body, due to motion there is kinetic energy because of its velocity. This kinetic energy will be converted to heat energy and it will be lost. Next, the frequency of vibrations depends on the size and shape of the body and remains constant. Here it is only depending on the size and shape of the body, and it will always remain as a constant. Here what is the case? The frequency of vibration is less than the natural frequency. Okay, when compared to natural frequency, here the frequency of vibration is less. It decreases in frequency depends on the damping force. Since the frequency, it is depending on the damping force, it is depending on the frictional force. Due to this reason, the frequency, natural frequency, when compared to the natural frequency, there is a smaller value. Now, the third type is forced vibration. The vibration of a body which takes place under the influence of an external periodic force acting on it. That is, we are continuously applying a force. An external force is being applied. In that case, due to this force, the vibrations are called the forced vibration. In case of forced vibration, there are three factors on which the forced vibration depends. The first one is a restoring force. As usual, there is a restoring force. Okay, that is the body's tendency to come back to its original mean position. Second, the frictional force. Frictional force will be acting because there is a medium. Now, the external periodic force or the driving force. This is very important. How much external periodic force you are supplying. So, here the external periodic force, the frequency of the external periodic force and the natural frequency will be different. If in the case of external periodic force and the natural force will be having, that is a natural vibration, the frequencies will be same. In that case, there will be maximum amplitude. Okay, so maximum amplitude is when the frequency of the driving force frequency will be equal to the natural frequency. Okay, when they become equal, there will be maximum amplitude. If the frequency of the driving force or the external periodic force is smaller or larger, that is different from that of the natural frequency, in that case, there will be, that is a vibration, the maximum amplitude or the amplitude will be different. That amplitude will be small and finally the body will come to rest. So, this is a case of forced vibrations. What are the difference between natural vibrations and forced vibration? Natural vibration, the vibration of a body in absence of any resistive or external force are called natural vibration. There is no external force acting. But when it comes to the case of forced vibration, the vibration of a body in a medium, here medium is important, here it is happening in vacuum, in presence of an external periodic force are called forced vibration. External periodic force or the driving force. Okay. Second point, the frequency of vibration, it depends on the shape and size of the body. These are the only factors on which the frequency of vibration depends. But here the frequency of vibration is equal to the frequency of applied force. Applied external periodic force frequency it depends on. Third point, the frequency of vibration remains constant. Here we know that in case of natural vibration, the frequency of vibration or the natural frequency is always a constant. Similarly, amplitude will always be the same. But when it comes to the case of forced vibration, the frequency of vibration changes with change in frequency of the applied force. When the applied force frequency changes, what happens? The frequency of vibration also changes. Next, the amplitude of vibration remains constant with time. We have studied the graph. In the graph, how it is? It is just increasing, decreasing. That is up and down. This is time and this is how it goes. That is height. This height, the maximum amplitude will always be the same. When it comes to the case of forced vibration, here what happens is depending on the frequency of vibration, it can first increase, decrease, then go again, increase, decrease, continue in this way. So, depending on the frequency of external force that is being applied, depending on the external force, it can be changing with time. The maximum, it can reach maximum amplitude, the amplitude can decrease, the amplitude can again increase to some peak value, again decrease to some other value. So, this can happen in case of forced vibrations. Have you used radio before? So, while using radio, we know that only when you tune you will be able to hear the sound, right? Only at some places, that is while tuning, you will be very careful that only at some places you will be able to hear the music. So here what is actually happening? So here the radio, it works under the principle of resonance. Now what is resonance? So resonance is a special condition of forced vibration. So here what is happening is when a body vibrates in a medium under the influence of an external periodic force or frequency that is equal to the natural frequency of vibration, the body is in resonance. So here there will be radio waves produce of waves, that is there will be a natural frequencies. So when you tune, what happens is the frequency, that is there will be a force, that is we are applying a force vibrations will be created, and the frequency of these force vibration, when it becomes equal to the natural frequency, we say that that is we will be hearing a voice with a maximum amplitude. So here if you take F as the frequency of the forced vibrations due to the external force, okay, and N as the natural frequency, then when F becomes equal to N, in that case we will be able to hear sound with maximum amplitude, okay, maximum amplitude, and this condition we call as resonance. Else, that is, if the frequency is less than the natural frequency or frequency is greater than the natural frequency, that is there is no match, they are not equal. In those cases, there will be different amplitude and the amplitude will be smaller. Comparatively, the amplitude will be smaller. Amplitude of the sound wave that is being heard will be smaller. Okay, so here for resonance to happen, the important condition is the frequency of the forced vibrations should be equal to the frequency, natural frequency. If this is not happening, in that case there will be only forced vibration. This amplitude is maximum only because here the energy is increasing. Energy because there is a force, that is due to this force, and this frequency becomes equal to natural frequency. The energy is increasing, and due to this reason we are hearing the sound with maximum amplitude. Okay, the frequency at which the body starts vibrating at higher amplitude, at maximum amplitude, is called the resonant frequency. So this frequency, that is when frequency becomes equal to frequency of force vibration becomes equal to natural frequency, we will be able to hear the sound with maximum amplitude or higher amplitude, and this frequency we call as the resonant frequency of the given body. Okay, if it is not matching, in that case there is only forced vibration, and after some time the voice won't be heard. Okay, there will be a minimum amplitude only. So we can say that resonance, it is a special case of forced vibration. It is the special case of forced vibration. It comes under forced vibration, not natural vibrations or damped vibration. Resonance is a type of forced vibration where the frequency of the forced vibration is equal to the natural frequency. Okay. Second, object is induced to vibrate at its natural frequency, or we make an object, that is we are providing an external force such that the body is made to vibrate at a frequency which is equal to its natural frequency. Let us understand an experiment to get a demonstration for resonance. So here you are taking two tuning forks which is mounted on two sound boxes. Okay. So here inside the sound boxes there will be air column. These ends are open. Okay. Upside of the tuning fork are kept like this. That is open ends will be facing upward. Now what is happening? Using a rubber pad or something, you are just striking the first tuning fork. Okay. When the first tuning fork A is stricken, you can see that in this experiment, the B tuning fork will also start vibrating. What will be the reason? Here resonance is being created. So here when you strike this tuning fork, what happens? Due to this vibration, inside the air columns vibrations, the particles due to the heavy surface area, what happens? The air inside this sound box will also start vibrating. That is, the waves, sound waves are created. The sound waves goes to the second box. Okay, here the sound waves reach and the particles here also start vibrating. Due to the vibration, tuning fork B also starts vibrating. So here what happens is when the frequency, here there is a frequency, it becomes equal to natural frequency, and the natural frequency will be equal to that is the frequency of the tuning fork B catches the natural frequency of the frequency of vibration of tuning fork A. In that case, both of these will vibrate with maximum amplitude. So this is the experiment. Okay, so the points, vibrating tuning fork A, it produces forced vibration. It is creating forced vibration because we are providing an external force here. Okay, in the air column of its sound box. So we are just providing an external force, and due to this external force, tuning fork A starts vibrating. It is creating a forced vibration on the air column that is in the sound box. Clear? These vibrations are of large amplitude because of large surface area of air in the sound box. Inside the sound box, you can say that there is a heavy surface, that is a large surface area. Due to these vibrations of maximum amplitude will be created. And this is the reason why tuning fork B also will start vibrating and the resonance will be created. Second experiment, forced and resonant vibrations of pendulum. Here you can see that on a string, a rubber string is taken using some threads or strings, A, B, C, D, 4 bobs are suspended. Okay, so you can see that A and B are of same length. When you check, you can see pendulum A and B are of same length. Second, D is longer than A or B. So A and B, they are of same length. You can see the D is more of length, that is length is more compared to A and B. What about C? C is shorter than A or B. So it's here in this experiment, C is shorter than A or B. A is equal to B, the pendulum length A and B are equal, and that of D is greater than that of A and B. So this is the experiment. In this experiment, what we are going to do is, we are going to just displace bob A. When bob A is displaced, let's see what is happening to bob C, B and D. Now let's see the observation of this experiment. So here you can see that C is of smaller length. We have frequency F is equal to 1 by 2 pi root of G by L. That is, frequency is inversely proportional to the square root of length. When length decreases, frequency should increase, right? So here the length is small, which means frequency will be high. Here the length is bigger, comparatively the length is higher, then in that case frequency will be small. Okay, now in this experiment what is done? A is displaced. When A is displaced, what happens? Forced vibrations are created in C, B and D. Okay, that is, the string will start getting some energy and it will start vibrating. All these pendulums will also start vibrating because of the force vibration that we are creating, the external force that we are applying on A. Now what happens is, when you take the case of A and B, they are of same length. They will start vibrating with the natural frequency of vibration. So, but initially B will be vibrating with a smaller frequency, but gradually what happens? It will be getting the same frequency, same natural frequency of that of A. Okay, A is now transferring energy to B. To reach, that is, to reach their values, they will be transferring energy. So here you have to remember, A and B will remain in phase. But what is happening? When A is having minimum amplitude, B will be vibrating with maximum amplitude, and vice versa. That is, when A is having maximum amplitude, B will be in minimum amplitude. That is, they will be going to and fro. If A is moving here, B will be going here. So that is how it will start vibrating. When you compare C and D, in C and D what is happening? In C and D, they will also be vibrating, but not with phase with that of A and B. So these are the points. Pendulum B also starts vibrating initially with a small amplitude, but gradually it acquires the same amplitude as pendulum A initially had. They will be reaching the natural, that is, they will be reaching the natural vibration frequency. The vibrations of pendulum B are in phase with those of A. They will be in phase. Third point, the pendulum C and D also vibrate with very small amplitude. C and D, they will be vibrating, but the thing is, they will be vibrating with very small amplitude. Clear? Now the third experiment or the third demonstration is resonance in air column. So here in this experiment, you can see that you have taken a cylindrical tube and a cylindrical vessel which are connected using a rubber tube. Okay, here it is being filled with the water up to a certain level. There is air, here also water and air. Okay, now what is done is, you are taking a tuning fork, a vibrating tuning fork is brought to the mouth of, we can call this A and this as B, to the tube A, mouth of tube A, we are bringing the tuning fork. Here what happens? Due to the vibrations in the tuning fork, they are creating forced vibration in the air column. So here there will be air particles. These air particles will start vibrating at its natural frequency. There will be water particle. These water particle also starts vibrating at the natural frequency, and suddenly you will be able to hear a loud sound. Okay, why? Because of this forced vibration, all the particles start vibrating at its natural frequency. When they start vibrating because of its natural frequency, what happens? There will be a loud sound that is being produced. So here you can see that the vibrating tuning fork is held above the mouth of tube A. It caused forced vibration in the air column of tube A, and this forced vibration is creating the loud sound. Difference between forced vibration and resonant vibration. First point, the vibration of a body under an external periodic force of frequency different from the natural frequency of the body are called forced vibration. That we have seen. Now what about resonance? What is the difference between the resonance and the forced vibration? Resonance, we know, is a type of forced vibration. Okay, the vibrations of a body under an external periodic force of frequency exactly equal to its natural frequency. Here it is not necessary that it is equal to natural frequency. Here it should be equal to natural frequency of the body, and then it is called resonant vibrations. Second point, the amplitude of vibration. Here the amplitude of vibration is small. What about this case? The amplitude of vibration is very large. It is very large because here the natural frequency and the frequency of forced vibration will be equal, and the body will have maximum energy and will vibrate with maximum amplitude. The vibration of the body are not in phase with the external periodic force. Okay, they are not in phase, but here it is in phase. The vibration of the body are in phase with the external periodic force. We have explained what is it. Okay, what does in phase mean? Next, these vibration last for a very small time after the periodic force has ceased to act. Okay, once the periodic force, the external force that we are providing is stopped, after some time the body will come to rest. Okay, the vibrations will stop. It is only for a small period of time. These vibrations last for a long time after the periodic force has ceased to act. Even though the periodic force has ceased or stopped, till the body will continue in vibration for a longer period of time. Now let's take some examples of resonance. This experiment we have discussed before, resonant vibrations of pendulum. So here we are taking two pendulums which are suspended using a rubber string. Okay, so you can see that here when you check this, when this stops, this is vibrating at a large amplitude. It is going to large amplitude. When this stops, this is vibrating at large amplitude. So here what is happening? We have explained this experiment, right? That is, when you create a vibration in A, what happens? Due to this vibration, the string will start vibrating and the energy transfer, there is an energy transfer happening, and here this will also start vibrating. So here you can see that they are in phase. Okay, they are in phase. You can see, just check this. With time, this is how the vibration amplitude is. You can see that if here we have maximum amplitude for B, then A is having minimum amplitude. At some points, what happens? That is amplitude, you can check, it will become same. Okay, here they are almost same. Here what is happening? The amplitude of B is decreasing and that of A is increasing. A becomes maximum, B will become minimum. That is, B will stop in that case. Again, what is happening? Amplitude of A is decreasing and A will come to stop, and B, what is happening? The amplitude is increasing and B will have the maximum amplitude. So just check this. Here you can see, now in this condition you will be having A is stopped, B is vibrating with the maximum amplitude. Here when B is stopped, A is vibrating with the maximum amplitude. Okay, if two pendulums of same length are suspended from a rubber string and one pendulum is made to vibrate, the other pendulum also starts vibrating with a large amplitude and in same phase because of resonance. So until it reaches resonance. Resonance means natural frequency and the frequency of forced vibration. Here, when you are displacing A, what is happening? A forced vibration is created by A on B. Clear? So once they reach resonance, they both will be vibrating. Only the difference is that when one has maximum amplitude, the other one will be having a minimum amplitude. Next is resonance in machine parts. When a vehicle is driven, the piston of the engine makes to and fro motion at a frequency depending upon the speed of vehicle. So when you are moving in a cycle, that is, you are pedaling a cycle, at certain speed what happens is you will be able to hear some sound and you will be thinking that your cycle is getting damaged, because here what happens is there is a loud sound produced because of resonance. That is, you are moving, that is the forced vibration that is being created and the vibration of the different parts of cycle, that is different parts of cycle will be vibrating with its natural frequency. When they become equal, there will be resonance happening. When you take the case of large vehicles, here again what happens is there is a to and fro motion of the piston. You can see there will be some fuel and the piston, there is to and fro motion. Due to this to and fro motion, forced vibrations are created. Okay, and different parts of the vehicle will be having, there is a machine's different part will be having natural vibrations. Okay, so this natural vibration, natural frequency, when it becomes equal to the vibrations of the, that is the vibrations of the frequencies of vibrations of the forced vibration, in that case what happens? There will be resonance happening and loud sound will be produced and you will be feeling that the machine is getting damaged. Next, third one, resonance in a stretched string and sound box of musical instruments and sonometer. So you have a sonometer where there is a sound box, okay, a big box in which there is air. There is an air column. So when you strike the string, what happens? Just to take the case of a stretched string. Okay, this is a string. When you stretch it, what is happening? When the natural frequency becomes equal to the frequency of force vibration, in that case, you will be able to hear a maximum sound. Okay. Now here again the same thing is happening. When you strike the string, it can only produce a very small sound. Due to the presence of air column, here there will be air particles. These air particles will start vibrating at its natural frequency, and due to this reason you are able to hear a loud sound. Even in case of a guitar, in guitar you can see the sound box. These strings are placed on a sound box. In the sound box, there is air column, there will be air particles which will be starting to vibrate at its natural frequency, and due to this reason what happens, the sound will get amplified. It will reach the maximum value and you are able to hear good sound. Okay, that is the sounds. The sounds amplitude is increasing. A louder sound is being able to hear. Fourth one, resonance in air column and tuning fork. This experiment, this demonstration also we have seen. So here what is happening? You are taking a tuning fork, which is vibrating tuning fork, is brought near the mouth of tube A. Here what happens? Vibrations are created to the air particles and water particles. They start vibrating at a frequency which is equal to the natural frequency of the force vibration. The force vibration frequency and natural frequency of the vibrations of air particles becomes equal. At that time, maximum sound is being able to hear. Okay. Next, resonance in the case of bridge. If you take the case of a suspension bridge, when soldiers are crossing suspension bridge, they are asked to, usually we know that left, right, left, that is they will be marching at the same pace. But what happens is, in that case, the vibrations, that is the force vibrations frequency will become equal to the natural frequency and the amplitude will become maximum, and due to this reason, there is chances for the suspension bridge to break. So in order to prevent this, the soldiers will be asked to break their steps. Okay, if they all march with the same space, what happens is, in that case, force vibrations can create the resonance, and due to this reason, the vibrations, that is the bridge, will start vibrating at maximum amplitude and it will be breaking. Next, resonance in radio and TV receivers. Have you ever imagined how you are able to listen to a music? You will be tuning the radio, only then you will be able to hear the music. Only at a particular points you are able to hear the music. Here actually what happens is, from the antennas, from different radio stations, what are created, there will be radio waves coming. Okay, they will be vibrating with a particular frequency. Now when you tune the radio, what happens is, you are creating, that is when it matches electromagnetic, that is electronic components, when you are tuning, there will be electromagnetic vibrations created. So when this electromagnetic vibration frequency becomes equal to the natural frequency of the radio waves, then in that case resonance is happening. Okay, due to this resonance you will be able to hear the music. Understand? The same thing is happening in case of TV receivers as well. Characteristics of sound. So when you are shouting in your class and suddenly your teacher comes in and she asks somebody to stand up and ask, why are you making sound? So how does she able to find who has made this sound? Because there is difference in sounds, right? When you take your case and your best friends, two other best friends, in that case you know that all of your sounds are different, right? You will be able to hear the sound and say who the person is. When you compare the sound of yours and your sisters, they will be different. When you compare the sound of yours and your mothers, they will be different. Yes, all the sounds are different. When you take two musical instruments, when you take a flute, a guitar, a violin, you can see that the sound they produced will be different. If you are producing sound at the same loudness, still there will be some difference. So there are three important characteristics for sound. The first one is the loudness. That is, a person who is speaking at a low voice and a person who is speaking at a high voice, they are producing different sounds, right? They are producing sounds of different amplitude. That is, the loudness is different. One is producing a loud sound and the other is producing a small sound. What about pitch? When you compare the sound of your father and mother, they will be different. One will be of a low pitch and the other will be of a high pitch. We will be explain what pitch is, and the quality of sound. We will be saying that if you go to some people, that is some sound engineers, they will be saying about some good quality sounds, low quality sounds, etc. So what does this quality mean? So we will be explaining in detail. So these three are the characteristic: loudness, pitch and quality. So what is loudness? Loudness is a word that you are familiar with. For example, if a teacher comes to your class and she will be taking class and she will be asking if the last bench students is able to hear me properly. Why not the first bench students? Why is she asking the last bench students? Because the first bench student will be able to hear it more clearly compared to the last bench students. What is the reason? Because the last bench students are at a greater distance. So the sound that is heard to the first bench student and the last bench student is different. There are 5 benches. If you consider 5 rows, in these 5 rows, the sound that is heard by each row will be different. So what is the reason? The loudness is different. So loudness is nothing. You can define loudness. It is a characteristic by virtue of which a loud sound can be distinguished from a faint sound, both having the same pitch and quality. So we have studied 3 characteristics. We have said about 3 characteristics. Even though the sound has, if you are considering a teacher, the teacher will be producing the same quality and same pitch sound, but that one heard by the first bench student and that heard by the second bench student and that heard by the last bench students will be different. So what is the reason? The first bench student will be hearing a loud sound, whereas the last bench student will be hearing a faint sound. So to explain this, let's consider an experiment. So here you are taking a tuning fork, a microphone, and you have a CRO. CRO is cathode ray oscilloscope, which is used to get waves. Okay. Here time versus displacement will be given to get the amplitude. If you are producing a loud voice, there will be maximum amplitude, and if it is a small voice or a small sound, then the amplitude will be also small. Okay, so you're striking a tuning fork and you are placing it here. What happens? The microphone, through the microphone, an amplification happens, and there you will be getting a wave. This is how the waves look like. So in some cases, you will be getting these type of waves, and in another case, you are getting these waves. Okay, here you can see the amplitude is high, here the amplitude is small. This is a loud sound and this is a small sound. Okay, so this is how you can explain about loudness of sound. Understood? Now, what are the factors on which loudness depends? So, we will be studying that important thing is loudness will be directly proportional to the square of amplitude. So, when you increase the amplitude, loudness also increases. If you increase the amplitude 2 times, okay, if you increase amplitude, if amplitude becomes 2A, then loudness will become 2A whole square, which means 4A square, that is 4 times the loudness becomes. If you increase amplitude by 3 times, if you make it 3A, then what happens? The loudness, amplitude is increased 3 times, loudness is directly proportional to 3A whole square, loudness will become 9 times the initial value. Okay. Clear? So here, this is how you can explain loudness, and loudness depends on the amplitude. Next, so what are the factors affecting loudness of sound? First one, the loudness of a sound heard at a place depends on the following 5 factors. One, we have said loudness is proportional to the square of amplitude. When amplitude increases square times, then the loudness will also increase. Loudness directly proportional to square of amplitude. Okay. Second, loudness varies inversely as a square of distance from the source. So, I am standing here, I am a teacher, I am standing here and I am producing sound. As the students, when you take 5 students, so this is first row, second row, third, fourth, fifth, and this is where I am standing. Okay. First row will be able to hear me properly. More louder sound will be heard by first. When you come to the 5th row, what happens? The sound will become faint. So here, loudness is inversely proportional to the square of distance from the source. Okay, it is inversely proportional to the square of distance from the source, and I am the source here. Okay, for example, if the distance, if it is increased by 2 times, okay, d becomes 2d whole square. Then what happens? Loudness, it is going to decrease by, that is loudness becomes proportional to 1 by 4 times d. Okay, so here 1 by d square is the initial loudness. When you have increased the distance by 2 times, what happens? When you take the square out, that is 2 square is 4, 1 by 4, 1 by d square. The initial loudness is proportional to 1 by d square, and the new loudness will become 1 by 4 times the initial loudness. Clear? So here, by increasing the distance, when you increase the distance, loudness decreases. When you decrease the distance, loudness increases. Okay. Third point, loudness depends on the surface area of vibrating body. So if you consider two vibrating body, one with less surface area will be able to produce small sound. Okay, that is, they are directly proportional. When area increases, loudness also increases. If you take the case of two speakers, small speaker or the bigger speaker, which can produce more sound? The bigger speaker, right? For example, if you are taking small Bluetooth speaker, you and your friends will be able to hear the sound. But if you are taking a large speaker that is used for marriages and all, that is, the people all around will be able to hear the sound. Okay. Now, the fourth factor is loudness depend on the density of the medium. We have studied three states of matter: solid, liquid, gas. Okay, we have explained this. In which case is the sound? If you are producing the same sound, in which case can you hear the louder sound? Louder sound is when the density is high, that is in the solid state. Okay, in case of solid state, what is happening? All the particles are close to each other and the vibration will be more, and therefore the sound waves can travel easily, therefore the loud sound can be heard. Okay, but in case of gases, the sound waves, the traveling will become difficult because particles are at longer distances and a faint sound will be heard. Loudness depends on the presence of resonant body. If there is resonant body, what happens? If you have taken the case of pendulum, A and B of same length, what is happening? They will be vibrating with the same amplitude, that is the frequency. They will match the natural frequency. Okay, and then what happens? The sound heard will be louder. So if you have resonant bodies, because of the frequency of forced vibrations matching the natural frequency, in that case resonance is created and the voice will increase, that is the loudness will increase. Next, the second characteristic, pitch. When you consider the sound of a boy and a girl, boy's sound will be having a low pitch and girl's sound will be having a high pitch. We say girl's voice have high pitch and boy's voice have small lower pitch. Okay, so here the characteristic by which a shrill sound can be distinguished from a grave sound or a sharp sound of same loudness. Here loudness and the quality will be same, but you can distinguish between the two sounds, because if if a boy and a girl, they shout at the same loudness or they are making the same sound, that is they are making the sound of same volume, but still you will be able to distinguish between these sounds because they are having different pitch. Girl sound has more pitch and boy sound have a lower pitch. Understood? So this property is called the pitch, or this characteristic is called the pitch. So this pitch, the characteristic pitch, it depends on the frequency. So when you take the case here, the wavelength is small compared to this case. Okay, so we can say that when wavelength is small, lambda decreases, we know frequency increases. Okay. So here when frequency increases, the pitch also increases. So when the frequency is high, then you will be calling the sound produced will be a high pitch sound. High pitch sound. Okay, when the frequency is low, that is when wavelength is high, what happens? Wavelength increases, frequency decreases. In that case, when frequency is low, what is happening? The sound produced will be frequency low. We say that the sound produced will be a low pitch sound. It will be a low pitch sound. Okay, here we have time. With time, that is the result that you are getting from a CRO, how the amplitude is varying. That is how the amplitude looks like, that between each crust, consecutive crust and consecutive trough, you will be having you can calculate the wavelength. Clear? So the factor on which pitch depends is pitch of sound. It depends on the frequency of wave. This pitch is usually taken in case of musical instruments. This different notes will be having different pitches. Next is the quality of sound. If you are considering two sounds or three or four musical, that is a sound produced by 3 or 4 musical instruments, if they are having the same loudness and same pitch, the sounds can be differentiated with the quality by knowing the quality of sound. So here we have different wave pattern. First is in the case of a noise, second the case of a music, the sound that is produced by a piano. In all these three cases, when you consider, you can see that the wave pattern is different, the waves are different. With that time, there is change in displacement, and this is how it looks like in the case of a noise. In music, it is like this. If you are taking the case of a piano, the music that is produced by piano, the pattern is like this. Okay, so here the waves are different, the wave pattern is different, the wave front is different, or the waveform is different. So in this case, we can say that quality is a characteristic which two sounds of same loudness and same pitch but emitted by two different instruments with different waveforms. The wave patterns produced will be different, is called the quality of sound. So the sound that is produced by a guitar will be different from a sound that is produced by a violin. That produced by a violin will be different from a sound that is produced by a flute. All these are different because they are producing different quality sounds. Okay, so this is about quality. You just need to understand, that is, you have to just study according to the syllabus the definition of what loudness is, what quality is, and what pitch is. Just the definition of the characteristics only we have to study in this chapter. Clear? That's all for today. In today's session, we have studied about forced vibrations, natural vibration and damped vibration. We have discussed about resonance and also the applications of resonance. Also, we have studied about the characteristics of sound. Hope you all enjoyed the session. I'll be back in the next session. Until then, stay tuned to LearnoHub. LearnoHub free hai par best hai. Thank you.